So, greetings, students. I hope we can get into today's lecture. Okay, so in today's lecture, we will be moving to the next part of your first unit, that is your admittance matrix. Okay, it is one of the important topic, and we will be dealing with the introduction to the bus admittance matrix in this lecture. So followed by that, we'll be getting to the algorithm for finding the Y-bus matrix in the upcoming classes. Currently, in this session, we will be dealing with the bus admittance matrix introduction part. Okay. So, as I already said, your power system is a interconnected network. It is an interconnected network, and it has a n number of branches and nodes, and these n number of branches and nodes comprises of your transmission line, transformers, and then your generators. Okay, so this you already know. And among this transmission network or the interconnected power system network, there lies three kinds of buses. Okay, there lies three kinds of buses. Among them, the first one is your generator bus. Okay, generator bus. It is also known as your PV bus. And from this PV bus, what you can do is it is possible to tap the. Sorry, it is possible to inject. It is possible to inject power into the network. Okay, if you're having a network, complex network in the sense, there must be a way for in and way for out. It is similar to the maze. Okay, similar to the maze. So in a maze, there will be a point of entry and a point of exit. Similar to that, over the complex interconnected power system network, there will be a point at which the power can be injected, and as well as there will be a point at which the power can be tapped out. And the point where the power can be tapped out is a PQ bus or a load bus. Generally, the load bus carries enormous amount of load, and this PV bus will be having the power injection tools like your generators and condensers. Okay, so moving on, as I said, there are three types of buses. In the previous slide, I have shown only two types. So starting with your PV bus and then PQ bus. Okay, PV bus is called as generator bus, and PQ bus is called as a load bus. And there's another one bus which is called as slack bus. So this slack bus acts as a reference. So as we have seen in per unit problems, in your per unit problems we have taken a generator uh, value to be the common base value, and if you are considering in such a way that if you're taking that generator means the generator which is connected to that bus corresponds to your slack bus or the reference bus. That is, uh, the power source which is connected to this slack bus or the reference bus will will be taken as your reference, and its base value and its base kV will be taken as the common base MVA and common base kV. Okay, generally you have like this slack bus refers to a reference bus. Okay, and the power system network can be simplified basically with two important tools. First one is Y-bus matrix, so that's what you're going to see today, and the second one is your bus impedance matrix. So your first unit revolves around these two matrices. So if you're forming the matrices Y-bus and the Z-bus matrix in the sense, it is very easy for you to for using the computational methodologies which you are going to see in the second and your third unit. Okay, so this is the initial step that you have to consider for the computational analysis of the power system network. So that's what they are saying. And moving on, So what is the need of the Y bus, and why we are using the Y bus? So we have to see that. So Y bus matrix helps in first thing. First point is that it is possible to analyze the load flow or the power flow studies with the help of the Y bus. Okay, so what are the things you can get from the power flow or the load flow analysis? So this power flow or the load flow analysis determines the value of your voltage magnitude, load angle, that is the angle between your load and your source side, then real power, reactive power, and then the current at various buses. As I said, your power system network is an interconnected system, so it is necessary to solve using computational methodology. Okay, and for solving those computational methodology, you need some parameters. Okay, so those parameters are determined through this power flow studies. So those parameters are nothing but your voltage, load angle, real power, reactive power, followed by your current. Okay, so this one you can do with the help of your Y bus matrix. And the next one is that optimal load flow analysis. Optimal load flow analysis is nothing but that is for this, the best example what you can say is that if you are in the city of Chennai, okay, you're in city of Chennai, and at the time what you can do is that it is more or less like scheduling your power. That is, you are in Chennai and you are going for your some other city like you can consider the south side, okay, Madurai, if you're going in the sense. So at that time what you do is for 1 month duration you are going for out of station. At the 1 month duration, you can even shut down the power at your home. Okay, but it is not practically possible in India. Then it is practically possible in countries like America and Canada, because there they are using the power utility to be as a prepaid quantity. It is more or less like your how you are topping up your mobile phone. Okay, you are topping up with the plans, right, for each month. So similar to that, in foreign countries, you can top up your power consumption. Okay, because in foreign countries it is entirely given to the private sector. Okay, it is the private sector who decides keeps the slab for each unit. Okay, so at that time what they will be doing is they will be in prior they will be scheduling the power. Okay, otherwise you can take it this way, that is industry is operating for 24 hours. Okay, so what the power system engineer at the substation will be doing is that he will be giving first priority to that industry when compared to that industry which is operating for nearly 8 hours or 6 hours. Okay, so there they are finding some optimal solution. Optimal means most efficient solution. Can be maxima or minima. Okay, uh, okay, so that it can be more economical, so that the load flow can be more economical. Okay, it a separate subject is there for you in your next semester, I think, power system operation and control. So that the entire subject revolves around this one single point. Okay, so at that time you will be studying in this subject, you will be dealing only with this first point. Okay, okay, moving on to the bus impedance matrix. So for what purpose they will be using bus impedance matrix means the primary point is they will be making use for your short circuit analysis. So you would you guys itself very well know that there might occur some blackout in the power system, okay, due to some fault conditions. Okay, so mainly whenever the fault occurs, the magnitude of the current increases drastically. Okay, so it is the responsibility of the power system engineer, the engineer at the substation, to locate these faults. And for that purpose, they'll be performing short circuit analysis, and a tool which is used for performing the short circuit analysis is your Z-bus matrix. And based upon this Z-bus matrix formation and the short circuit analysis, you can it is possible for you to arrive at the rating of the circuit breakers for protection criteria. Okay, if you're having the correct circuit breaker rating means it will be very easy for you to protect the and island the system. So moving on, the injected bus and the current of the power system under steady state condition can be related through your Y bus and Z bus. So now we are coming to the relationship between your Y bus and your Z bus. So it is more or less similar to the normal formula what we will be using. So nothing but the Ohm's law, V equal to IR, right? V equal to IR. So if you're having your I at this side, in the sense I equal to V by R, and this 1 by R represents your Y. Okay, so this is what over here they have given. Okay, and for the second one, V equal to IR is what this equation is. Okay, so we are speaking about matrices. Why it is necessary to speak about matrices? Because as I said, it's an interconnected power system, and you have to see through the each point connection between each buses. Okay, I'll be moving on, so you'll be understanding with the diagram I have drawn, which I have drawn. So as per the diagram, if you are connecting one bus to other bus means there must be a connection, and that connection must be represented through a matrix format. So I'll be moving, so you'll be able to understand. So this is the bus. So for example, if you're having a two bus system in the sense, so this will be your bus 1, this will be your bus 2, and if there is a connection between your bus and Y bus 1 and Y bus 2 in the sense, and this connection is represented by Y12. Okay, so the bus is connected between your first bus and your second bus, so that's this component. And Y11 represents the self admittance carried by this bus. Okay, carried by this bus, so which is Y11, and Y2 represents the self admittance which is carried by this second bus itself. And here can extend this up to the n number of nodes. Okay, so as per this, if the nodes are represents n, so we'll be having that much nodes within the network. So this is the definition for your Y bus admittance matrix. Okay, so that is Y bus matrix or the current. Y bus matrix or the current that flows into the nodes of the network when unit voltage source is applied between a bus and the reference bus. What they're saying is very much easy to understand this definition with respect to the equation. Okay, as you know, you already know this equation: Y bus equal to Y bus into V bus equal to I bus. So what they're saying is that this Y bus directly represents your current. Okay, it directly represents the current. Current usually flows into the node, right? So this flows into the nodes of the network when unit voltage source is applied between a bus and reference bus. So when this V bus is contributing to a unit value, in the sense that is, if the V bus is equal to 1, then your Y bus will be equal to your I bus. Okay, if your V bus equal to 1, then your Y bus equal to your I bus. So that's what the with respect to the definition. Okay, Y bus matrix are the current that flow into the nodes of network when the voltage source is applied between the bus and the reference bus is 1. So this is with respect to the definition. Okay, so coming to the elements, I have already shown you the Y bus equation. Okay, so it has nearly diagonal elements. It has diagonal elements, right? It has diagonal elements, and apart from diagonal elements, it also has off diagonal elements. Okay, so what you can infer from that kind of Y bus matrix in the sense, so diagonal elements are called as self admittance. So usually it corresponds to the respective bus. Okay, so it is also called as short circuit drawing point admittance. So this also you just have an idea. Okay, how you can find this? It can be found by applying a unit voltage, the same point what you have seen with respect to the definition. Unit voltage source between the ith bus and the reference bus. Okay, and measuring the current flow into the ith bus. So with respect to the definition, you will be making this V bus to be 1, and you will be finding this I bus. So this contributes to your Y bus. Okay. So while dealing with the algorithm, I'll be showing you. Coming to the off diagonal element, so it is called as short circuit transfer admittance. It's called as short circuit transfer admittance. So how it can be found? It can be found by applying a unit voltage between buses. So over there, the previous case or your diagonal element, what you have seen, it is applied between your bus and the reference bus. But over here, it is applied between two buses. Okay, here is if you can see Y12 in the sense it is corresponds to two buses. Okay, and measuring the current flow in the jth bus. Okay, so if I and J are not connected in the sense, you have to consider that admittance to be zero. In some cases, what happens is that first bus will be there, second bus will be there, and third bus will be there. In some cases, what happens is that the 1 and 2 will be connected, and 2 and 3 will be connected, and 1 and through 3 there won't be any connection. In such a case, y1 through will be corresponding to 0. Okay, y13 will be corresponding to 0. So moving on, basically the bus admittance matrix Y bus matrix is a symmetrical matrix. So symmetrical matrix means you'll be having upper triangular matrix, lower triangular matrix, right? So you know about some matrix calculation. We'll be dealing with the matrices in this unit. Okay. So you just have in mind that generally Y bus matrix is a symmetrical matrix. So symmetrical matrix in the sense if there is a quantity of Y12, okay, Y first bus, second bus is there. So Y12 is connected. Then if it is symmetrical matrix means it is Y12 will be equal to Y21. Okay, and hence the values will be mirrored. Okay, for maintaining the symmetricity property. Okay. Okay, coming to the sparse matrix. So sparse matrix is similar to the thing what I have said. That is, in most cases, all the network will not be connected together. Okay, each bus is connected to only a few nearby buses. Okay, only it will be connected to a few bus, and so most of the off diagonal elements will be zero. So in the sparse matrix, what you can see is that if the off diagonal elements are zero, most of the off diagonal elements are zero, then you can consider it to be a sparse matrix. So this will be considered as a special case. Okay, this will be considered to be a special case. While dealing with the problem, I'll be telling you about this. Okay, and now we'll be dealing with the Y bus matrix that is how you are formulating the Y bus matrix you'll be dealing. So after this, I'll be telling you the algorithm. Okay. So this is a mathematical analysis, and the method used over here is direct bus inspection method. So it is the method which is used here. So here you can see we are considering a three bus system. We are considering a three bus system. Okay, consider to consider the 3-bus system. Okay, and the voltages are V1, V2, V3. So this is how the bus looks like. So the current flow between your first bus and your second bus is I12. Wait a minute. Okay, first you can consider a 3-bus system, and over here the voltage for the first one, second one, and third one is V1, V2, V3, and the current flow from your first bus to your second bus is I12, and corresponding to your 2 to your 1 is I21. From your 1 2 3 is 1 3 1 3, and then 3 1 and 3 2. And another one thing what you can see is that here the admittance value y12 will be equal to your y21. Why? In the sense your admittance matrix is basically a symmetrical matrix. So based upon that, it is uh, based upon that it is symmetrical. So what is our aim? So our aim is to arrive at the equation of y bus equal to y bus into v bus equal to I bus. So we it is our aim to arrive to this equation from the given diagram. Okay, it is a theoretical part. So sometimes they might be asking you to derive. So in such a case, you use this this 3-bus system. Okay. So first we'll be applying KCL at node 1. So this is your node 1. So at the node 1, the current entering, as per the KCL, it is the current entering a node will be equal to the algebraic sum of the current leaving the node. So here it is the node, so it is entering, and from this node the current is leaving. So your I1 is equal to I11 plus I12 plus I13, right? And with respect to your admittance, okay, so how we can write this I11 is that, so your I11 can be written as it is a here it is any self admittance. So 11 corresponds to the self admittance. So as per your self admittance, so what you have to do is you have to subtract the voltage with your reference voltage as per the definition. Okay, so it will be V1 minus V0 into Y11. So Y1 corresponds to the self admittance of your bus 1. Okay, and after this your I12 corresponds to V1 minus V2 into Y12. At the same time, your I13 corresponds to V1, okay, minus V3 into Y13. Okay, so these are the current values. Now you have to apply over here, to apply in the equation. And now what happens? Your I1 will be equal to V1 minus V0, okay, into Y11 plus V1 minus V2 into y12 plus v1 minus v3 into y13. So now you have to multiply inside and you have to take it common out. So in such a case, what happens? Your I1 equal to so v1 is common over everywhere. So what happens is that your y11 you can take your v1 common, so it will be y11 plus y12 plus y13 into v1, okay, minus of v2 into y12 minus of, okay, minus of v3 into y13. Okay, consider this to be your equation 1. And over here, what you have to consider is that for the formation of a Y bus, okay, for the formation of a Y bus, there's a particular formula, that is YII, that is formation of a self-admittance matrix YII, which is equal to summation of I equal to 1 to n, okay. So YIJ,
Sir,
yeah, tell me.
sir, can you explain what happened to V not Y11, sir? Once again.
From this step to this step, right?
Yes, sir. Yes.
Okay, fine. Okay, we'll be just multiplying inside. So it will be v1 y11 minus v0 y11, okay, plus v1 y12 and then minus v2 y12, okay, then plus v1 y13 minus of v3 y13. Okay, we are just multiplying each and every admittance with that of the voltage. Okay, we are just multiplying this with this with this, and this with this. And after multiplying, here it is very clear that you can take the common out. So what you are going to take common is, the first thing you are going to take the common v1. So if you're taking v1 common means I1 equal to, so from here it is y11, okay, and from here it is plus y12, and from here it is plus y13 into your v1, okay, and for the second term it is y12, okay, uh, sorry, for the second term it is it corresponds to your v2, okay, so v2, so where's your v2 value? Here it is. So it is minus, so it will be minus v2 into y12, okay, again it will be minus this term v3 into y13, and over here you might be asking what happened to this value. Okay, so it is a reference value. So you can just leave it. Okay, so it is a reference value, so you can just leave it, because mostly the reference what will be over here will be of 0. So for the reference node you can take it to be this voltage to be 0. Okay, so if you're omitting this, so you'll be getting the equation as y11 into v1 plus y12 into v2 plus y13 into v3. So how this comes means, so this entire will be matrix will be correspond to your self admittance matrix, and this corresponds to your transfer admittance matrix, and this also corresponds to your transfer admittance matrix. So how it is possible means using the formula. So are you now clear with this? We are just omitting this reference value of v naught, will be getting this equation. So consider this equation to be your first equation, and take this equation to be your second equation.
Sir, how can y12 and y13 in V1
Yeah,
can be transfer
yeah, transfer
admittance?
to like this. Yeah, I'll be saying there's another formula for that. I'll be next writing with it. So you just I'll be giving 2 minutes. You just see through this. For the next one, there's another one formula. I'll be saying. Okay, I'll be now moving. So as I said, so how you can consider your YII is that your YII is nothing but your diagonal element. It is a diagonal element. Okay, so this diagonal element corresponds to the self admittance. Okay, self admittance, and generally it is how you will be getting is it is sum of the admittance of all components connected to ith bus. So for here, so with the self admittance of the first bus, what happened is that what are the bus disconnected the self admittance, which is first one is for the y11, it is y11 plus this y12, okay, this y12 plus this y13. Okay, so these three admittances are connected to the particular bus. Okay, that is your first bus. So as per that, you will be getting this matrix, and there's a generalized formula for that. And if you are getting with respect to your y2 second bus, it will be y22. Okay, and here it will be coming with small y21 plus small y22 plus small y23 followed by For y33, it will be y31 plus y32 plus y33. Generally, you can write this in a common methodology as yii will be equal to summation of j equal to 1, okay, j equal to 1 to n yi of j. So based upon this formula only, we are writing all the other self-admittance matrix. Okay, so you have to have in mind that capital Y corresponds to your summation of all the other admittances which is connected to the particular bus. Okay, whereas small y corresponds to the particular admittance which is connected between the two buses. Okay, connected between the two buses, but whereas for y11 it is a summation of capital Y, in the sense it is a summation of all the other uh, buses. Okay, so this is what with respect to this. Based upon this only the second equation comes out. So for the second equation, so y11 plus y12 plus y13 corresponds to y11, and over here this small y12 over here it corresponds to y12, and here it corresponds small y13 corresponds to capital Y13. So for self-admittance matrix alone, you have to consider in such a fashion. Okay, you have to consider all the other admittances which is connected to it. So I'll be moving on. So next is you have to apply KCL. So we have completed the first node, and now we'll be going for the second node. Apply KCL at node 2. Okay, node 2. If you are applying KCL at node 2 means what happens? So your I2, so this I2 will be equal to I2 equal to I21 plus I22 plus I23. Okay, so now we have to write with respect to your admittance. I2 equal to V2 minus V1. Okay, V2 minus V1 into Y21 plus V2 minus, it is a reference, so V0. So it will be Y22 plus V2 minus V3, and over here it will be Y23. Okay, so upon rearranging, as per the previous case, we'll be getting I2 equal to minus V1 Y21, okay, plus Y21 plus Y22 plus Y23 into V2 minus V3 into Y23. Okay, so now we have to write this as I2 equal to so I'll be moving on. So here your I2 equal to Y21 V1 plus Y22 V2 plus V23 V3. This will be your third equation. So similarly, you have to form for your for node bus 3. Okay. So similarly for bus 3, so that you just calculate. Okay, I'll be finally writing the final one.
So
So
for
for
minus y21 and minus y23, you will rewrite it as capital Y21 and capital Y23 as well.
Yes, man. For self admittance only, you have to go for summation. Okay, for self admittance only, you have to go for summation. Otherwise, for transfer admittance, so this corresponds to a transfer admittance. So for transfer admittance, you can directly write it. Okay, and over here I forgot to say. So for the transfer admittance, you have to take a minus out. That is, uh, if you're taking the minus means you'll be getting it. So for the transfer admittance, so in the to this we have seen for your self admittance, right? For self admittance you have seen, and for the transfer admittance, what happened is that here you might be asking here actually if you are coming out means here there's a minus and here there's a minus. So what is a part is, so y ij. So we have seen for y ii, and for yij what it is, that means yij equal to, you have to just consider a minus of yij. Okay, so if you want to know how this equation and this equation are coming out means you just refer with the book. Okay, uh, time permits I'll be seeing through it. Okay, but as per the computational point, you just know about this much. Okay, for transfer admittance, this is the formula. You have to put minus of small yij, but for self admittance you have to make a summation. Okay, and similarly for bus 3, so your I3 value will be equal to, I'll be just directly writing, you just formulate it by yourself. So y31 vi v1, y31 v1 plus y32 v2 plus y33 v33, sorry v3. Okay, so over here we have got, and this you can take it as 4. So from equation 3 comma 4 comma 2. Okay, equation 2, so this is your equation 2. What we have got is, we have got 3 equations with 3 unknowns. Okay, we have got 3 equations with 3 unknowns. So it is very easy that you can form a matrix. Okay, 3 equation with 3 unknown. So the matrix look like I1, I2, I3 equal to y11, y12, y13, y21, y22, y23, followed by y31, y32, and then y33 into v1, v2, v3. So from the 3 equation 3 unknowns, you can form the matrix equation in this format. So this contributes to your I bus equal to y bus into your v bus. So this was our aim at initial condition, to come arrive at this equation, and from this we have arrived with this equation. Okay, so this is the thing you have to consider for the, okay, you have to consider for formation of y bus. So in the next one I'll be dealing with the algorithm, how you can use the algorithm, step by step algorithm for formation of y bus. So there's another one thing with respect to your self admittance. So another one point, just note it out. A self admittance, for medium and long transmission line. Okay, long transmission line, you have to include shunt admittance. You have to include your shunt admittance. While dealing with the problems, we'll be getting a clear idea. So if you're including a shunt admittance means what happens? Your YII will be equal to summation j equal to 1 to n YIJ. So this is the thing what you'll be generally using for your shunt self admittance. Apart from that, you have to add your shunt admittance. So if the line is a medium pi line, mostly they'll be giving medium pi line. Okay, so this you can take it as a first one, and moving on, this you can take it as a second one. So if it is a medium pi line, your capacitance will be split up. So your capacitance will be split up into Y shunt 2 by 2. Okay, so you just have this in mind. So in the next class we'll be dealing with your algorithm. Okay, so the next class will be of